Hello everyone, and thank you for joining us here today for Precision Digital's Fundamentals of PID Controllers presentation, where we talk about using, selling, and specifying PID controllers and give you information that you need to know in order to work with or sell or specify these types of controls. Before we get started, a couple of points logistically I'd like to go over. The first one is that, as you have probably noticed, everyone here today is in listen-only mode. There are too many people on the line for me to just have a bunch of open phone lines. And so if you would like to ask a question, which I will take during the presentation, and we'll stop periodically to review them, if not then at least at the end. If you'd like to contact me with questions, I'd ask you to type it into the chat box that is in the lower left-hand corner of your screen. If you're on mobile, I believe there's a button on your phone that will let you open up that chat interface. Also, the most common two questions that I get are, can I get a copy of the slides? Or will I be able to see this video later? And the answer to both of those questions is yes. You will both get a copy of the slides and a recording of the video. And you'll get those emailed to you by mid-next week. It'll take us a couple days to process the video, but then we'll email that out to everybody. And it'll also have a PDF of the slides. Finally, you would be doing me a great favor if you would fill out a survey that you may see should it pop up at the end of the webinar or when you leave. It's always nice to get feedback on how we're doing, get some ideas that you may have about other things you'd like to see, or just get feedback in general about your thoughts on these presentations or the topic. With all that out of the way, let me introduce myself. So my name is Joe Ryan. I'm the VP of Sales and Marketing at Precision Digital, and I've been in the process industry now for about 15 years. I actually started doing product design and development. In fact, I worked on PID controllers. That's one of the first things I did once I got into this industry. And so I've got a lot of experience with applications, panel mount displays and controls, and specifically PID controllers. With that, one of the issues with PID controllers people are having today has nothing to do with the product. It simply has to do with getting it. So I'm curious, are you having any delivery issues with any non-Precision Digital PID controllers where maybe our SuperNova PID controllers may be able to help you? If you go ahead and click yes here, certainly I appreciate knowing that. We're happy to reach out and see if we can swap a SuperNova in for your application. So know that we may be in touch. But also it's just nice to kind of see where people are at with various deliveries. And not surprisingly, there are a lot of you out there that are having problems with PID controller deliveries. Maybe not most of you, but a lot of you. And so hopefully the information you learned today about the SuperNova will help. So what is on today's agenda? Well, first we're going to just talk about what is a PID controller. What the heck does that term mean? What do they do? What do they look like and feel like? We're going to take a look at some common PID controller terms and features. What is unique to PID controllers that you'll need to know if you want to be able to specify them or talk intelligently about them? We'll take a brief look at what is and is not a good application for PID controllers. You'll understand what is PID control and what may not be PID control where you don't really need one of these. Or perhaps the times you're not doing PID control, but you do still want a PID controller. We've got a list of need-to-know questions that will help you make sure that you're getting the right PID controller. And we'll take a brief look at the end at the new SuperNova line of PID controllers, our PD500 PID process and temperature controllers from Precision Digital. So let us start with the question, what is a PID controller? And to help me shape this discussion, perhaps you can share with me, have you ever sold, bought, or used our original Nova series of controllers? That would be our old PD540 through PD570 series. The assumption there, of course, being that if you have worked with these, then you may know something already about PID or PID controllers. But it looks like most of you have not, and that's not surprising. This is a fundamentals of PID controllers presentation, so I wouldn't expect a lot of PID experts to be out there. So then let's start at the beginning. What is the PID part of PID controllers? Well, I'll say right up front here, this is not a class on PID. That is in and of itself a major topic for controls engineers. So we're not going to get super in-depth, but to put it simply, PID control is a method of controlling the output to a system, or coming up with what the output to a system should be, It is a math algorithm. Simple as that. It's a bunch of math you do, including integrals and derivatives and such, that tells you what your system output should be in terms of 0 to 100%. You know, this is just raw math, so it has nothing to do with what signals you're looking at or anything like that. It says 0 to 100%, what does my output need to be in order to maintain a level in the system? So what does that output really mean in terms of the process industry for people attending here? Well, that output could be driving a solid-state relay to control a heater. It could be sending a control signal to regulate a power controller to run a larger heating element. It could be positioning a valve, not a value, but a valve, in order to bring in hot water, bring in cold water, move steam, what have you. It could be controlling a motor speed or a fan speed. It could be running pumps for level. There's all sorts of different devices involved in flow level, temperature, and pressure that these could be providing an output to. That having been said, the same concept is present on all of these, right? You want to provide a system output that will be used to control a flow level, temperature, or pressure, or other measured process. That's all you're doing with PID. You're calculating what the output needs to be to control that system. So what does PID actually mean? Well, the P stands for proportional, the I stands for integral, and the D stands for derivative. Those are the three different parts of that PID algorithm. The idea being that you're going to have a proportional part, which is just comparing, is my process where I want it to be? How close to where I want my process to be, or the PV is my set value that I want to try to attain? And certainly that's the easiest part to understand. As you get closer to your set value, your proportional value is going to go down. Integral and derivative tuning, now we're talking about actually looking at a window in time. It's no longer just a snapshot. And what those will do is help you to adjust based off of system disruptions. It will help you to adjust as your system parameters might change, all while trying to minimize your overshoot, yet get to the process, get to your process target value as fast as you possibly can. So it's actually a fairly complicated control system, but those are the three elements in it. And in theory, each one of these can be individually set. So to understand how that control methodology is going to work, you have to understand a couple of terms. In a PID control algorithm, you're going to have your process variable, your PV is what it's called. And that's what appears on the front of PID controllers. That's usually the largest display that shows up. By the way, I do want to pause here for 1 second. I have a question. Someone has asked, is the output that I referred to in that slide always an analog value, 4 to 20 milliamp, or can it be a digital or an on-off? Well, it certainly can be something other than an analog value, and we're going to take a look at that in a few slides. But it's a great question. So I'm talking about 0 to 100%, but that 0 to 100% does not mean it has to be a 4 to 20 milliamp signal or a 0 to 10 signal. It can be other types, and we'll talk about those in a few minutes. So as I was saying, so you've got your process variable, your PV, and that is what you are currently reading. Could be coming in from all sorts of different sensors, right? It could be coming in from thermocouples, RTDs, voltage or current transducers, various transmitters. But whatever it's coming from, that is your live process value. So if you're trying to control level, that's your level. You're trying to control temperature, that's your temperature. Then you have your set value, or your SV, or perhaps your set point, which is an SP. It's all the same thing, the SV, the SP, just different terms people use. And this is the desired process variable. So if this is your actual temperature, this is what you want the temperature to be. And then you've got your manipulated value, or your MV. And that is your output percentage. That's where this algorithm says, you know what, whatever my output is, whatever mechanically that signal is, it needs to be at 75% to work. And so if you have to be at 75% and you happen to be a 4 to 20 milliamp signal, you're going to set it to 16 milliamps. And the controller says, I think this manipulated value will take the process value and bring it to this set point. So now that you've got your set point as an input and you've got your PV coming in, you can see the difference in those things. That gives you your error, and your error gets fed into your P, your I, and your D algorithms. You take the output from those three function blocks, those three individual algorithms, and you get yourself your controller output. So that's real basics of what PID actually is and how that works. There's other terms you should know as well to work with PID. There's a gain or an alpha parameter that you see a lot of the time on PID controllers. There's also auto-tuning and manual tuning. So I'm actually going to go through these backwards a little bit. I think it's a little easier to understand. So manual tuning is where you are entering in your P, your I, and your D values. If you are attending this webinar, do not do this. If you are not an expert and understand what that PID algorithm is all about, do not start trying to punch in numbers and see what they do. Maybe as you get familiar with it, you might edit existing numbers that come from an auto-tune, but don't just jump in and start screwing around with those numbers. You're not going to get the results you want. So I would just recommend you kind of stay away from that. What most modern controllers do, including the SuperNova, is what's called auto-tuning, where the controller itself will run an on-off cycle of the control elements, and then that's going to tell you what your P, I, and D values are. So the controller actually determines those values for you, and you don't have to just start guessing what they should be. Now, once you're done your auto-tuning, then you can start making changes to your gain or your alpha parameter. And what those do is let you make slight changes to the response of that PID output, that output percentage. So here, for example, you can see a alpha at 50. So if you were on a SuperNova controller, we're entering it at 0 to 100%. Well, you can enter in your alpha, and let's just say your alpha is at 50, kind of in the middle. That's going to give you, in this case, a nice smooth approach to your process variable over time, or to your set point rather, and then you're going to maintain it to that level. But if you find that you're getting a lot of overshoot, or you find that it's taking you too long to reach your set point because it's being too cautious, well then great, you can adjust your alpha parameter, and that's going to allow you to change that response. So that's why you see these three different curves here. It's sort of showing you three different ways your process variable might respond based on changing that alpha parameter, which adjusts your output. So really all you need to do if you were to have an application for these today is implement the auto-tuning once your system's all wired up, let it run through its on-off cycles, and then if you like it, great. If you don't like it, you adjust your gain. You adjust that alpha parameter. So now that we know what PID does, we know what that math kind of functions to do, let's talk for a minute about what is not PID. And these are still valid control types, and often people will choose PID controllers for these, but it's not really PID. On-off control is the most common non-PID control element the PID controllers are used for. And what I mean by not PID is an on-off control is essentially just a 0 or 100% state output. It's not time proportional pulses. It's not 4 to 20. It just is on or off, and it's purely based on how close my set value is to the process variable. A great example of this is your home thermostat and heating system. You've got a thermostat in some hallway somewhere or in a bedroom, and you set it, and your home heating system will, if I just kind of make a chart here, let's say this is my set value, right? I set my temperature to be a 72-degree set value. Well, your house is going to heat up some, and it's eventually going to reach that set value. And then once you're 1 or 2 degrees over, it's going to turn off. It's going to let the house cool down a bit. And when it hits 70 degrees, let's say it's going to turn on. And it doesn't really matter how long that takes. It's just going to get you into that cycle of on and off, all based around where I am in relation to my set value. With a PID algorithm, you're able to say, hey, you know what, I want to turn on my baseboard heaters at 72%. Well, obviously, home systems don't support that. They're on-off control. If you could, you could say, hey, I just want to get up to that 72 degrees, and I'm going to heat just enough to keep myself level. But you don't. That's not what on-off controls do. So on-off control is a perfectly viable way of controlling processes. It's just not PID. The other one is alarming. People oftentimes just use alarms as control elements. Hey, I want an alarm to go off when I reach a certain temperature. When I hit a certain level, I want an alarm to go off. I want to turn on a pump. Okay, great. Really what you're doing there is you're using your alarms to function as on-off controllers. And again, that's a fine way to do it. We'll talk about that in a little bit, but it is not true PID control. So then what is a PID controller? Now let's talk about what actual PID controllers are. So in theory, a PID controller is really any instrument that uses PID algorithms. Now what you see here is a bunch of various DIN-sized, mostly panel mount, one DIN rail mount PID controllers with displays. Those are your traditional PID controllers, but in reality, a PLC could be a PID controller. A SCADA system, a program running in a control room could have PID elements into it. You could probably have PID elements in LabVIEW. Anything that implements this PID algorithm to get an output and use that to drive a system is a PID controller, technically. However, generally, people are talking about things that look like this. That's when someone says, hey, I want a PID controller, they don't mean a PLC. They mean a device that looks like one of these devices. These are specifically designed to do usually single, sometimes multi-loop control in a very easy way. It's very simple to interact with for operators. They come in a variety of shapes, sizes, and appearances. Everything from here's a 1/8 DIN vertical 1/8 DIN SuperNova, or you can get DIN rail mount ones, or you can get quarter DIN units or 16th DIN. You'll see them in a second. There's all sorts of different ways you can get them, but they all sort of look similar. PID controllers are now part of a larger control system, because now we're not just talking about the math algorithm that is PID, we're talking about the actual controller. And so you've got your PID controller, which is going to be wired up to provide some kind of a control output to your process. And this is usually going to be a pump, a fan, a power controller, a motor driver, something that's going to have a direct impact. So to use a real simple example, if I'm trying to control the temperature of, let's say, a heat trace, well, I'm going to be driving a relay that's going to be pulsing on and off the power to the heat trace element. And in that case, this process element would just be the relay, right? It would be the relay driving the heat trace. But then I'm going to have a temperature sensor hooked up to that heat trace element, so I can bring the temperature back into my PID controller. And so when you hear me say things like a single loop controller, that's what they mean. They control one process loop. Now, you could have, say, a dual loop controller that essentially is just this thing times 2. But that's a more complicated device. Most PID controllers you're going to run into are going to be single loop controllers. Provides an output to the system, which makes changes, which you measure, which you bring back into your controller. Boom, there's your single loop. Now, of course, a couple other things in here to notice. You've got your process variable, right? So that is my thing that I'm measuring. That's my flow level, temperature, pressure. And you also have disturbances coming into that process. If you're trying to control temperature of a heat trace element, well, the exterior temperature is going to have an impact on that, and that's going to change over time. Wind is going to change that. If you are trying to control a level, well, the more things you pour into this tank, the more things that go into that are going to obviously make changes to the system. So one of the reasons you use PID is that it can account for these disturbances in the system. I mentioned PID controllers all sort of look similar. You can see them, and you know what they are when you see them. But they are all different sizes, and all those standard sizes have terms for them. So here on the right, you'll see our Trident 1/8 DIN meter. Most of you are probably familiar with that. That's our 1/8 DIN horizontal unit. So it's wider than it is tall. PID controllers tend to be available, like these SuperNova units you see here, in larger and smaller sizes. So you've got your quarter DIN unit, which is a larger square. It's essentially twice the 1/8 DIN. You can see how the math on that works. Twice a 1/8 DIN would be that quarter DIN. Then you've got your 1/8 DIN vertical, where it stands upright. And then half of the 1/8, you've got a 1/16 DIN. There are other sizes as well. There are 3/16 DINs. There are 1/32. These are the three most common from my experience. These are the ones that Precision Digital offers in the SuperNova line of controllers. But it's important to note that you could have the same family of controllers available in multiple sizes, and that's something to keep in mind when you're speccing. Other common design elements you're going to run into in PID controllers, they are often IP65 fronts. That is compared to NEMA 4X. Somewhat equivalent. It's proof against water ingress up to certain pressures and volumes. It's dust tight. But because PID controllers are very much universal in the way they look, the bezels tend to be designed a certain way, and so they tend to be IP65 versus NEMA 4X. However, it is worth noting that Precision Digital offers NEMA 4X enclosures you can put these in, so while obviously this is still only IP65, NEMA 4X, having seen the testing done, I would say NEMA 4X is superior to IP65 for water protection. And so if you're putting it in a NEMA 4X enclosure, you're all set. And so if you just wanted to put one of these somewhere, you get a NEMA 4X box for it, you're fine. They're two different standards. They're not 100% equivalent, but as far as putting it outdoors, being proof against water protection, if you put it in a NEMA 4X box, you're fine. You're going to maintain that IP65 without a problem, assuming your cutouts and such work out. A few other very common features you're going to find on PID controllers. They're going to show you the set value and the process variable right on the display. So here's an example of our 1/4 DIN SuperNova, which is a very great looking display. The display itself looks very modern and is great, but as far as what's on that display, very common elements, right? You've got your process variable, which is the process I'm reading now. In this case, I'm reading degrees C, and so here you've got your actual sensor element coming in being read by the display. Then you've got your set value, which is what I'm trying to control too. And so you can see in this case, my process variable isn't quite at my set value. Looks like I'm off by about 8 degrees, and so it's not very far given we're talking hundreds of degrees. And so as I'm approaching that set value, my manipulated value, my MV, is getting low. My heating output is only 17% because it's going to slow down to just maintain that temperature at what it needs to be to keep that 538 degrees. Oftentimes people will want to switch between auto and manual control, so there's usually some means to do that. Ours is particularly easy. We put right on the front of the faceplate how you do it, and all you have to do is hold the set and the down arrow, and it will allow it to switch between auto and manual control. So if I find 17 degrees is what I need to be at, or 17% output, but I just want to heat it up a little bit right now manually for some reason, well, I could put it in automatic control and just increase that percent output manually. And when I'm all done, I put it back into automatic control, and it goes back to controlling to my set value. Now let's talk about the actual I/O, because I know there's been another question about that in the meantime, and I think these slides will answer all those questions. First, you've got your inputs. PID controllers will generally provide universal inputs. That means they're going to take in various voltage ranges and 4 to 20 milliamps, which you need an external resistor for. On the SuperNovas, for example, you get that resistor automatically. Other controllers that require resistors you won't, but generally the inputs will take in voltages, which means you need that resistor to take in a current, because they also read temperature. And so you also have the ability to take in various thermocouple types. Most controllers will take in a wide range of temperature inputs for thermocouples and RTD curves. One thing worth noting here is that not every controller takes in every input type. What you see here is the long list from the SuperNovas. It's worth confirming that if you have something other than, say, a JKE or T-type thermocouple, you check and make sure your controller can do it. If you really have an application need for a U or a B, keep an eye on your controllers for those. If you don't recognize the thermocouple type, it's worth confirming that the controller you're connecting it to can do it. That's understood. Most people seem to get that. The control output types, though, I see a lot of confusion around. So let's talk about those for a moment. Your control outputs are usually 3 major types. You've got what's called SCR. That's the term you're going to see in manuals and specifications and ordering guides and things like that. Well, SCR just means it's a 4 to 20 milliamp output. The SCR is an old term. It stands for silicon controlled rectifier, which is the type of output that you use for a specific design of power controllers, I think is where that really comes from. But all it means is you're getting a 4 to 20 milliamp output. So when you see SCR used somewhere, they're talking 4 to 20 out. Now, those of you in the audience here, many of you use control valves, motor controllers, pumps, all kinds of other process devices that are going to use this 4 to 20 milliamp out to control something. between 0 and 100% on or off. And that's fine, right? SCR, it's just a legacy term. So don't really worry about what that means. If you're working with a valve that the position of which is determined by a 4 to 20 milliamp signal, great, you want an SCR output. It is worth noting, though, that these SCR outputs are very commonly driven by less than a full 24-volt power supply with a lot of oomph behind it. So if you are using that output and you are driving it to something that needs a lot of voltage, you're not going to use this output for that. If you require 24 volts, say, to move the valve, you're not going to in any way be able to tap this SCR output for that. You're going to need a separate power supply to run that device. The other type of control output you're going to have are SSR, which stands for solid state relay, which just means it's a solid state relay driver, which means the actual output itself is a voltage pulse. It pulses on the voltage over a certain duty cycle, over a certain period, in order to sort of rapidly turn on and off whatever the controlling device is. So this is a time proportional on-off cycle. So you set a period, and let's use a short period and say that's going to be 1 second. You probably don't want to click an electromechanical relay on and off every second. So instead, you use this solid state device, which is going to pulse the voltage. There's no moving parts. There's no breakdown. It can go very fast without having any kind of problems. There's no arcs. There's no sparks. And you're going to use that voltage pulse with power controllers, heaters, and other quick on and off devices, usually through an intermediate solid state relay. You're not going to use the small signal SSR coming out of the controller directly to turn on a heater. You're going to use that to drive a solid state relay that's an intermediate relay that is going to be the thing turning on and off the heater. Heaters are a great example for this because while you may not want to rapidly pulse a valve on and off, that's not going to work. If you're just turning off, say, 120 volts going to a heating element, yeah, that's perfectly fine. You can pulse that rapidly and could use that pulsing power to control the heating element. Relay control is essentially the same thing as a voltage pulse if you're using the PID element of it. It's a time proportional control over a period. So, 75% output in a 1 second period would mean that it's going to stay on for 0.75 seconds and it's going to turn off for 0.25 seconds, and then it's going to just continue that cycle. You don't want to go that fast with relays, though. So generally there are limits on how quick controllers will let you operate those relays. I think on the SuperNova, for example, it's 2 seconds minimum, but I wouldn't even recommend that. So generally people get a relay control output when they just want to do on-off control. They like the idea of having all those display elements. They like the idea of having the process variable there. With a set value they can change, seeing if their control elements are on or off right now. So this would just be 0 or 100%. They like all that. They like the ability to just hit the set button and use their up and down arrows to change the set value. All that ease of use sounds great. They don't really need PID, but who cares? Now they can change their set point for the on-off control really easy. They can see the status of their system, so they get a PID controller even though they're not technically doing PID. That's usually what the relays are going to get used for. And that's great, right? We offer a SuperNova controller with a relay control output, and people often use it for just on-off control. And it's easy to set up like that, and that's a great way to do it. There are a lot of other outputs and inputs available for controllers, so here's some ways those can work. Generally, the SuperNovas would have all of these, but some of them they don't. So I made some notes as we go through this about things where it doesn't apply to the SuperNova, just as a side note. So you've got alarm outputs. Those are often called sub-outputs, SUB. So you might have like output 1, which is a relay, but then you have sub 1 and sub 2. Well, what the heck is that? Those sub-outputs are specifically meant to be alarm outputs. So you may have a control element, for example, a control relay that's a single pull, double throw, normally open, normally closed relay, but you find out, oh, those sub-outputs, those are just single pull, single throw. In fact, they may be single pull, single throw, and they may all have a shared common. So a sub-output is an electromechanical relay meant to be used for an alarm, and it might have different specs than your control output, so you want to keep an eye open for that. It's also worth noting that alarm outputs on PID controllers have a special kind of alarm called a deviation alarm that you wouldn't find on, say, a panel meter. And the deviation alarm specifically is designed to work based off of the difference between the set value and your process variable, your process variable. So for example, here we have a low deviation alarm. And this arrow over here is going to represent my set value. And because this is a low alarm, okay, let's assume that we are sort of at my set value. Well, as my temperature is going to go down, let me change my ink color here. My temperature goes down, I hit my alarm value for the deviation alarm. I say, oh, I've hit my alarm value set point. That's too low. Then it turns on the alarm. It starts to heat up again. And depending on how you set up the dead bands, at some point it's going to turn off, right? But you'll note there's no numbers here, right? The advantage of the deviation alarm is that it doesn't matter precisely what your set value or your PV are. All that matters is the difference. So if I set up a deviation alarm for 10 degrees below my set value, as the operator changes the set value, that deviation alarm is going to change with it. And so it's very convenient for control process alarms. It's also worth noting that there's a special mode in these controllers called standby mode for these alarms. Because the assumption is that you're going to be turning these on and off often, you're going to be changing set values often, a standby mode alarm means that you're going to ignore alarms that come about because somebody changed the set value. Well, you can say, hey, look, I know the set value is going to cause my alarm to go off. So I don't want that to trigger it. I want to give it a chance to get to that set value and then show me some alarms. I know I'm going to turn this pizza oven on and off every night. So, I don't want my alarm to go off because I turn it on in the morning and it's at room temperature. I know I'm going to be at low temperature at that point. And so it won't trigger when you have power on. So it's a way to eliminate some very common alarm conditions that you just take for granted. You say, I know that I'm going to go into alarm in these states. Ignore those states. You can do latching alarms. And a lot of time people are looking for limit controllers, which are very much devices that look a lot like PID controllers. All a limit controller really is a deviation alarm controller. As the set value changes, that becomes your new alarm point, and it has latching in there. So you use a latching with clear algorithm that says, okay, I will only allow my device to be manually acknowledged once the alarm triggers if I'm back in my OK condition. And so any of these controllers could be used as limit controllers. There are special FM limit controllers, if any of you are familiar with those, and obviously for that you need an FM approval, which most PID controllers, including the SuperNova, will not have because they're PID controllers and not limit controllers. But if you don't need that FM limit controller, most PID controllers can do that limit control function. And then they also have this thing called a loop break alarm, which is designed to tell you when your loop is broken, when that control loop is broken. So you may remember that I had a graphic back here. Nope, that's a little too early. Give me 1 minute here. Here we go. That talked about that single loop, right? The controller gives an output which changes the process, which you measure and bring back into the controller. Well, a loop break alarm says, hey, look, I have had my control output at 100% now for some time. And yet despite that, I am not seeing any change to my measured value. So something in this process, something between my output and what that sensor is reading, something over in this area is broken, and I should set an alarm off because this just doesn't make any sense. That's sort of your descriptive value of what those loop break alarms are all about. Obviously, they have high alarms, low alarms, things like that, but you're likely all familiar with those, and so I won't go into that, but these are kind of some unique alarm elements of PID controllers. Other terms you're going to run into: heating and cooling. Heating and cooling, again, like many of these terms, is based on the fact they kind of come from the temperature world, but can be used in really any process. All it means is that you've got two control elements. So let's use a temperature example. Let's say you have a water bath you're trying to heat. Well, you can add cold water to bring the temperature down. You can add hot water to bring the temperature up. And so really you could be controlling either one of those valves depending on where your set value and your process value are at, your process variable are at. And so a heating and cooling controller has the ability to provide two outputs, one for the heating side and one for the cooling side. A standard thing like, say, a pizza oven only has the control in one direction, right? It's just I turn on the heating element. And if I need to cool, I just let natural cooling occur. You don't drive a separate cooling side device, but sometimes you do, and that's what heating and cooling is all about. It's worth noting on the SuperNovas that generally I would not recommend people bother with heating and cooling controls unless you absolutely need it. It makes them sort of needlessly complicated for people to set up and get working. However, on the SuperNova, what we decided to do is find a middle ground where you get heating and cooling ability standard, but it only comes into play if you enable it. And the only cooling side output we offer on the heating and cooling mode is a relay output. So if you want to, say, have a 4 to 20 out or a relay out to control your heating side, great. On the cooling side, we just do on-off control. We just provide a relay output, which in theory could be a time proportional pulse, but generally would be a relay on-off output. Because oftentimes that's what we see. If someone is doing heating and cooling, they may be using a 4 to 20 out to control the heating elements, but then for cooling, all they're doing is just opening a valve, letting in some cold water into a heat exchanger or whatnot. So output 2 on the SuperNovas is always reserved for that cooling side output if you need heating and cooling. And if you don't, you just don't go near that, and the unit's set up to be just a one-directional control device. Other common I/O features that are available on PID controllers, you got Modbus and RS-45. Many now have software. The SuperNovas do as well. We have a really convenient front accessible USB connection on the larger sizes, not on the 16th DIN. On the 16th DIN, it's in the back of the panel, but that's really great for being able to go in there with the software and make quick changes after installation. You can also use them to measure multiple units and to monitor multiple units using our PC software if you have an RS-45 multi-drop system. We do not have them on the SuperNova, but some of the PID control units do have Ethernet, if that's a feature that you're looking for. And we've also got a remote set value input. Let's say you don't want to have somebody pushing buttons to change that set point. You could bring in a 4 to 20 milliamp signal or a 0 to 10 volt signal, and you can use that signal to set your input remotely. And so to do that, how might you do it? Well, you might be sending in a signal from a PLC, or you might somewhere have a set point generator. And these are examples of some of Precision Digital set point generators, where somebody could just turn a dial and ramp the set point up and down by turning this dial, which sends a 4 to 20 into the remote set value input, which changes the set value on the controller. Other common PID controller features that you won't find in panel meters. We'll go through this slide fairly quickly here. Process variable, set value, and MV displays. We talked about that. You've got more on your display than just your PV, which is what you'd have on, say, a Trident. Auto manual switching, we spoke about that. Ramp up and down is settings that allow you to change the pace at which your set value changes. So if I go from 100 degrees to 200 degrees, maybe I just don't want to cause system shock by cranking my output to 100% immediately. You know, if I'm opening valves or I have a very sensitive process here, I might want to slowly ramp up that 100-point change in my set value, and you can set those times and how that works. We talked about ramp and soak programming. That's obviously different. The remote set value inputs, which is unique to PID controllers. Cascade control is a means of linking up multiple controllers to try to control more complicated systems, and there are controllers that are designed to do that. For some reason, probably just because they're all based on one popular original PID control design, all the PID controllers I've worked with that are your standard panel mount style from all sorts of different manufacturers have this group programming style. So you have like an input group with all the input programming parameters into it, and an alarm group with all the alarm programming parameters in it. And they all sort of use the same setup style. So once somebody is familiar with one PID controller, it's not much of a challenge to switch to a different one because they're 90% the same in all cases as far as how you program them. Many of these PID controllers are only offered with a high voltage AC power supply input. So for example, to power a SuperNova, you have to have 120 or 240 volt AC. You don't have a 24 volt version to operate it. Some do, many do not. And then lastly here, a lot of PID controllers are UL recognized versus UL listed. UL listed is sort of a standalone device. UL, for example, a panel meter. UL recognized means that you are a component in a UL listed system usually. So If you're a UL panel shop and you're looking at PID controllers, you're looking for UL recognized. That is what the approval would be. But it looks different. It's kind of an odd-looking symbol here. And so it's just worth showing it to you to know that when you look at the side of a SuperNova and you see this, that is what UL marks look like for a UL recognized product versus your sort of more traditional UL that you might see on a precision digital panel meter, a lamp, an extension cord, a power strip, etc. But if you're a UL shop, that's the recognized mark you're going to be looking at. So to summarize all the things you need to know if you wanted to specify a PID controller, let's take a look at this list. What it really boils down to, before I get into any of these numbers, is this element here on the left. Ask questions. To really know what PID control features you need, you have to understand the whole system. What kind of output am I sending to what kind of device? Do I need a relay? Am I doing on-off control? Am I controlling a valve? What's going on here? What am I taking in for an input? What am I measuring? And so here are questions that if you can answer them will equip you well enough that you should be able to specify a PID controller for basically any system. First, what type of control is being done? Have them describe to you, okay, I'm going to make a change to my set value, and then I expect this to happen. You got to know if it's PID, is it on-off, are they just looking to alarm the system? What are the specific control styles they want to use here? What's the main PV input from? Am I measuring a temperature? Am I measuring a level, a flow? If I am, well, now that I know that, what kind of signal is it? Is it an RTD? Is it 0 to 10 volts? Am I bringing in a 4 to 20? You got to know that. How is that process variable being controlled? What is the thing that's going to change to adjust that process variable? Am I opening a valve to add water to a tank? Am I setting an output to a power controller that will control a heating element? Once you know that, you'll know what kind of mechanical signal or what kind of mechanical output or what kind of signal output you need to drive that thing from the PID controller. So you'll know what kind of control output signals are needed. It's worth checking that this is one directional or heating and cooling control. Are they just driving that number up or down, or do they have a means to drive it in both directions? Do they want anything other than just control? Do they want alarms? Do they want Modbus? There's plenty of other features you could get on these. Size and format is an important one. Many locations you already have PID controllers, and you don't want to try to replace a broken 16th-in PID controller from 20 years ago with a quartered-in PID controller that doesn't fit in the hole. So do yourself a favor and know the size of the thing you're trying to replace, or know what's already in the panel, because that way it's going to be an easy swap out. If I go back to the original photo from this presentation here, you can see, okay, great, I've got a 1/8 in cutout down here for a Trident panel meter, and then these are all quartered in cutouts. This plate that you see around this center one is probably because it was the wrong size. They probably had a larger unit in there, and then they got to make an adapter plate. How are you going to seal that? It becomes a hassle. So know the size of the unit that you want for the panel that you have. Do I need other I/O? Software setup, monitoring, any other kind of communications. Because there's no 24-volt power supplies on these, because they're actively driven 4 to 20 milliamp outputs and they're not really designed to run transmitters, things like that, you don't have a 24-volt transmitter power supply like you might on a ProView or a Trident meter. So know how you're going to run all the elements in this system. What's going to power that valve positioner? What's going to power that level transmitter I'm bringing in? What's the power I'm bringing into that flow meter? And know how you're going to answer that question. How are you going to get that power? And lastly, ask them how they want it to operate. Just have somebody describe it for you. Are they looking for ramp and soak programming with various profiles that change over time? Just run program 1 and let it run this recipe. Do they need it to slowly ramp up when they change the set point? You ask a nice question like that, or you think about that question yourself, you'll get a better understanding of the system so you can make sure you've got the options you need. So briefly, what does Precision Digital have for PID controllers? Well, we have our new SuperNova line, our PD500 line. The 510 are 16th in, the 520 are 1/8 in vertical, and the 530 are quartered in. They are very much the same. There's a couple of minor differences. the display is too small to show the output value on the 16th in. On the 16th in, the USB connector is behind the panel rather than through a sealed stopper on the front. But mostly these are the same types of units, right? So these are auto-tuning. You know what that is. It does its own PID calculations for you. Process and temperature controllers. They've got a very striking reverse polarity LCD display. Very happy with the way these look. You'll feel like you have a modern unit when you look at these. And they're not just 7-segment displays. They have 14-segment displays, so they can display characters very well. You have thermocouple and RTD inputs. You get your voltage and current inputs. All the same part numbers, so you don't have to worry about that. And we've got SCR, that's your 4 to 20. SSR, that's your solid-state driver, your voltage pulse. And we've got mechanical relay outputs. We've got that second control output we talked about that's used if you do have a heating and cooling application. It just comes standard. Lets you use a relay for cooling control. We can easily switch between auto and manual, something people very often are looking for in PID controllers. In fact, it was probably the #1 asked for feature that wasn't really present on our old Nova line. We've got the remote set value input and free programming and monitoring software. Taking a look at the prices, these are the prices for our 16th DIN model. Prices for the line actually start at $221. I'm sorry, that's the 16th. These are our prices for our quarter DIN model. Our 16th DIN unit actually starts at $221, slightly less expensive than the quarter DIN. But it gives you an idea of what the price ranges on these look like. And to order them, what you need to know is figure out your DIN size, right? So now I know we're looking at just the quarter DIN units. Figure out what your main control output type is. So if I know that I have a quarter DIN unit, so that's the size that a customer is going to be happy with that I'm working with. And I know that they need a 4 to 20 milliamp output. Well, as their main control output, they're going to use it to control a motor controller. Well, great. So now I've only got 3 model numbers to choose from. You'll notice that this part of that model numbers options are all the same on each one. So my only real questions are, do I need RS-485, a 4 to 20 milliamp retransmit, or some digital inputs to change between pre-programmed set points? Or do I need that 4 to 20 milliamp remote set value input? If I don't need any of those, I go with my base PD530A. So hopefully that process of picking a part number made a lot of sense to you because we just covered all of these terms. I do want to give a special warning for people, okay? This is a question we get asked a lot. Hey, can you cross over this Watlow XYZ? Can you give me a cross for this Eurotherm ABC? The answer to your question is kind of. There's a lot of features in PID controllers. Most of them are not used. And every manufacturer has a slight different standard combination of those sort of rarely used features. So when you give somebody a data sheet for PID controllers, say, can you cross this? There's a really good chance the answer is yes. But if you don't get the complete story, you run the risk of making a mistake. So for example, if someone were to try to cross a SuperNova unit over to a Watlow unit, well, is this a heating and cooling unit or not? Because a SuperNova could be. They could be using that cooling relay output. Probably they aren't, but they might be. And they need to know the story of the application and know if they should be quoting a heating and cooling unit or not. It works the same way the other way around. When we try to cross from other people, they're all a little bit different. So get the complete story before anybody calls us up and says, oh, hey, I'm looking to cross this. Here's my part number. The first thing we're going to ask is, okay, great, tell me about the application. If you want to purchase PID controllers, you want to see our stock, you can do it all online. Go to predig.com, look up the PID controllers, just do a search model numbers for PD500, and you'll get all kinds of results there. You can click on any one of them and bring you to the SuperNova page. From there, you are able to check our live stock. You are able to see what our lead times are. So, for example, this one down, this one at the top here that I circled. This is at the time we took this screenshot. We had 27 of those units in stock. If you wanted to buy more than 27 units, or those 27 units suddenly sold out, we could get more 5 business days after ordering. If I go look at the website right now, the very first one listed here, PD510-A, that's our 16th DIN unit with a 4 to 20 milliamp control output. We have 107 in stock. If we were to suddenly run out of those, we could get more 5 business days after ordering. So you can check all of it online. You can get price. For those of you who are resellers in the audience, you can get your price if you sign up on the website. You can get stocks. You can get lead times. You can build yourself a quote. You can buy them online. So my last question for you is, would you like Precision Digital to reach out to discuss our SuperNova line? Is there anything you'd like to discuss as far as new applications you might be working with, or maybe providing you alternatives to parts you're having trouble getting? Go ahead and click yes here if you want somebody to reach out and talk with you. All right, great. Thank you for joining us here today, folks. I know it took some time. Appreciate you sticking with me. Hopefully it was well worth your time. I do have a couple of questions here, so I'm going to cover at least a few of these before I go. But if you are leaving now, please fill out the survey. Should that appear for you, I'd really appreciate the feedback. Tell us how we're doing. Tell us what you'd like to see. That would be great. So let me talk about a couple of the questions that we have here. Can you buy a PID controller with a remote display where the operator can read the PV and set point without being able to punch the buttons to change them? So that is a great question. What I would suggest you probably do in that case, if you just want a remote display, there's a couple ways you can do it. You could use the 4 to 20 milliamp output and send it to another panel meter somewhere else. In the case of, say, a SuperNova, you would only be able to do that with one of those values because we only have one 4 to 20 milliamp output. But there are controllers out there in the world that you would have the ability to have two 4 to 20 milliamp outputs. But if all you're doing is trying to get a device that you can kind of lock out from people, so you don't want to give them access to the PID controller because you don't want them changing the set points, what I would suggest you do with a SuperNova is you just use our lock feature. It's a button combination. It locks the unit so you can view it, but you can't make any changes to it. And that would probably be the easiest way for you to give someone access to seeing what's going on without giving them the ability to change it unless they knew how to get it out of that lock. Another question here is the loop break alarm set by time duration? And that's a great question. I believe it is. I think that's actually a parameter that you could set up when you're setting a loop break alarm. In fact, I'll look that up real quick here just to make sure that I know what I'm talking about. Let me see here. Yes, a loop break alarm has some time delay parameters that you can set up that lets you define what that looks like to know when there's a problem. So you would give it some amount of seconds that it waits to know, okay, I'm not seeing a change here. It is not changed by enough percent. And so now I want you to give me that alarm. Another question we've got here is, can I get a 24-volt power supply similar to the PD765 to run the transmitter for the input? Well, and the answer to that is no, not on the SuperNova. These do not have that separate isolated 24-volt power supply output in order to bring in or give power to, say, a level transmitter and bring that back. So when you're using a PID controller, some PID controllers do have a loop power supply, but I'll tell you the ones I've seen, it's not something like you'd see on a PD765. It's not a 24-volt output that can give you 200 milliamps. You sort of program the analog output to be a loop power supply, and so you get like 18 volts that can maybe push just over 20 milliamps. I don't like them. You know, they're not really designed to be isolated power supplies, so I don't recommend people do that. So generally with PID controllers, I would say if you need a power supply, just get a power supply. Whether it's SuperNova or not, that would be what I would suggest. Let's see here. Any other? There are a couple of questions here about PID control, which I think are a little complicated for the audience. So those of you who asked those, happy to get in touch with you after the webinar to discuss them, but I'm not going to get too much into that here. And so I think with that, given it is 11:55, we will wrap up here today. I thank you, everyone who stuck with us here till the end. If you have any questions, please look me up, give us a call, go to the website and start a chat. Whatever means you'd like to get in touch with Precision Digital, please feel free to do so. We would be happy to talk about these PID applications, especially as everybody knows we're doing these webinars. We are ready to handle them. So hopefully I will talk to some of you soon. You'll get your email next week with the slides and the video recording. And I hope to talk to you all soon about PID controllers and how we can help you find the right one for yourself. Thank you very much. Hope you all have a good weekend.